Our next talk is going to be on biomass combustion ash in carbon capture, and it's going to be given by Mike. So Mike is a first-year PhD student at Brunel University. He is currently working on biomass combustion ash in carbon capture project, which is supported by the UKCCSRC Flexible Funding Call. He obtained his previous degree from Mendeleev University of Chemical Technology of Russia, where he focused on initiating explosive substances. So I'll just hand over to Mike now for his presentation.
Thank you so much. So I hope you can see my screen.
Yep. Yes, we can see your screen.
Okay, great. Thank you. So hello, everybody. My name is Mikhail Gorbounov, or just simply Mike. And today I would like to talk to you about biomass combustion ash in the context of post-combustion CO2 capture. The concept of bioenergy with carbon capture and storage, BECCS, is regarded as one of the most prominent techniques to mitigate climate change. And in fact, over 85% of the scenarios outlined in the IPCC 2014 report that keeps the temperature rise at bay, shall we say, implement BECCS initiatives as a tool for combating global warming. The favorable carbon neutral properties of the energy crops lead to them being widely used nowadays. For instance, Drax, a colossus in the British power sector, has already shifted 4 out of 6 of their boilers to burn biomass, and they're also planning to end coal use by the end of 2021, converting the last 2 standing coal-fired power plants to biomass combusting ones. So the feedstock is becoming more and more desirable, and currently the global biomass production is between 5 to 8 billion tons per annum. However, combustion of this feedstock leads to ash formation, with a mean ash yield at about 6.8%, which would equal to around 500 million tons of BCAs every year. However, BCAs have different properties to coal ash: elevated alkali earth, metals, oxides, hydroxides, carbonates, and more mobile hazardous compounds. Such properties render second applications, for example, cement, unsuitable, but the same properties do make them much more attractive for employment in selective adsorption of CO2, for example, as a precursor to desorption media. Such usage of biomass combustion ashes would decrease the landfilling costs associated with this type of waste, and their availability on site of biomass-powered plants slash massively the logistics costs. However, in order to be viable, the ash has to immobilize carbon dioxide. Therefore, biomass combustion ash has been extensively characterized and its properties assessed in the context of post-combustion carbon capture. The investigated industrial-grade BCAs can be divided into 2 main groups: fly ash and bottom ash. In this slide, you can see our materials. So let's begin with the characterization of the fly ash first. The surface morphology of the raw fly ash has been evaluated using the scanning electron microscopy, or SEM. As can be inferred from the slide, the fly ash consists of a mixture of spherical particulates with widely varying size, agglomerations of these particles, and some porous matter as well. The spherical particles are typical for fly ashes and can be attributed to their amorphous coating formed as a result of relatively abrupt post-combustion. As clearly demonstrated on the image on the right, though, there are stark differences in the various particles present in the fly ash, as well as the presence of some porosity. Apart from the morphology, the sample, the elemental composition of the sample was studied using the EDS technique. And this method facilitates an understanding of the elements present in the material. On the slide, you can see the spectrum taken from our fly ash sample. As can be inferred from the picture, the material mainly consists of aluminium, oxygen, and silicon. These are the prevailing elements in the investigated ash, and such results were expected. Apart from that, the main constituents of this potential adsorbent are alkali and alkali earth metals, such as sodium, potassium, magnesium, and calcium, with potassium and calcium being most prevalent across the conducted tests, as well as some iron and carbon. Gold can also be clearly identified from the scan. However, the fly ash sample has been covered in gold coating by a sputtering technique prior to analysis in order to negate any possible charging. We have also taken the FTIR spectrum of our investigated fly ash. One thing to bear in mind, though, is that this technique is perhaps not the most suitable one for identification of inorganic and mineral phases, as the reason being that the covalent bonds are more prominently displayed on the spectra than ionic bonds. The reason for this phenomenon is the fact that strong ionic bonds do not vibrate strongly after infrared absorbance, i.e. do not change their dipole moment during internal vibrations. And therefore, these vibrations cannot be easily detected. Nevertheless, the two outermost left peaks and the two other peaks in the middle were ascribed to the OH bond. This functional group is visible on the spectrum due to one of the two reasons. It is either denoting the presence of physical water on the sample, or it occurs there naturally due to the hydroxides present in the ash. Apart from that, the double bond between the C and oxygen are present in the carbonyl group has been identified. This functional group, however, is not exclusive to organic materials and can be seen in the carbonates that are proposed to exist in our biomass combustion ash. Furthermore, silica-oxygen bonds were also identified within the FA. In fact, the relatively low wave numbers at about 1,700 reciprocal centimeters suggest the silica-O bonds to be present in an aluminosilicate structures. This red shift phenomena occurs here due to the substitution of some silicon atoms with aluminium atoms within the formation. This change leads to a lower binding energy between the oxygen and silicon atoms, thereby decreasing the vibration bands from around 1100 for silica or silica compounds to a lower wave number for silica or aluminium compounds. And the same can be said about the band happening at about 700 reciprocal centimeters. We have also analyzed the sample using the Xray diffraction technique, and the results are presented on this slide. The investigated material is, as expected, a mixture of silicates and aluminosilicates with an abundance of inorganic mineral phases such as metal oxides and carbonates. Of particular interest is the potassium carbonate. K2CO3 is believed to be a substantial contributor to chemisorption of CO2, as in the presence of moisture, the potassium carbonate transforms into potassium bicarbonate, also known as percarbonate, which only has one potassium atom, and this allows for an additional carbon dioxide molecule to be fixed on the other K atom from the original molecule. Similarly, K2O is also a noteworthy compound. Again, in the presence of moisture, the reaction with CO2 leads to bicarbonate formation. Therefore, one molecule of potassium oxide supplies two atoms of K, each of which could attach to a bicarbonate ion, thereby contributing more to the capture process on the scale of per molecule of substrate than an oxide or a hydroxide of a bivalent metal. Nevertheless, magnesium oxide still can't go unmentioned, and in the conventional calcium looping process, this chemical, which is also seen in our fly ash, is used as an additive to the capturing media in order to improve cyclic stability. Plus, the carbonation reaction occurs at much lower temperatures for magnesium oxide in comparison to calcium oxide. Though calcium species are still valuable for carbon capture and are also present in our material in the forms of calcium oxide and calcium hydroxide. Calcium carbonates exist as well within our fly ash, and well, however, the limestone will not contribute in the post-combustion context of carbon capture because it has already most probably fixed some of the CO2 emitted during combustion process as it was formed within the combustion unit by binding the GHG molecules to the calcium-rich molecules of the biomass feedstock. Additionally, we have conducted a BET and BJH analysis, and the typical BET surface areas of ashes is believed to be in the region of 2 to 6 square meters per gram, with the coal ashes tending to have a smaller surface area in comparison to BCAs. However, the investigated fly ash appears to be much more porous than others reported in the literature. The specific surface area of our fly ash is approximately 9.4 square meters per gram. In contrast, the BJH cumulative pore volume is calculated to be about 0.01 square centimeter per gram, which is well within the reported range for ashes, both biomass and coal. The average pore diameter is estimated at about 7.3 nanometers, which is consistent with the EU PAC technical report, which specifies that for type 4 isotherms, hysteresis occurs if the pores are wider than 4 nanometers, and if the tests are conducted under nitrogen and 77 Kelvin, which they were. And the difference between the absorption and desorption pattern is clearly identifiable from the slide. Having extensively characterized the fly ash, our research group has looked into the applications of this material for direct carbonation. Unfortunately, the results were not as promising as would have been desired. We have then tried combining the fly ash with various additives, and this approach did yield a more positive outcome. However, it was not economically viable on an industrial scale. Therefore, our next step is to look into zeolite synthesis as means to valorize this waste. On the slide, you can see the preliminary results of our endeavors, which we'd love to report during one of the upcoming sessions, but we'll cross that bridge when we get there. Moving on now from the fly ash to the second investigated waste material, which is bottom ash, or BA. Generally, BA consists of three main constituents: the unburned biomass, the ash itself, and the unburned carbon. Therefore, we have aimed to extract the carbon, and the resulting material is pictured on the right there, which was denoted as BA63. And we can report that the extraction process yields good results, as the ash impurities sum up to just under 7%, and the moisture content is around 6%, with the rest being volatile organic compounds and a fixed carbon. Here are the SEM images they do depict the nature of our BA63. As can be inferred, the ash is mainly carbonaceous, with rare inclusions of glassy silicate spheres. The presence of carbonaceous species is clearly shown in the top picture. Furthermore, these assumptions were further confirmed by a carried out ETS analysis. And the energy dispersal spectrometry did corroborate the theory that carbon is the prevailing element, as data similar to the one presented in the top figure has been acquired throughout the sample, making the image shown representative of the bulk of the material. However, there were also constituents that have been found within the obtained BA63. Once a beam of light was aimed at the spherical particulate situated within our carbon, we can see a number of other species appear, as presented in the lower image. The analysis confirms that these spherical objects, as seen in the SEM, are of glassy origin, containing mostly aluminium and silica. Additionally, silver is also seen on the spectrum, but it is there because silver paste was used as the conductive adhesive utilized for this analysis. And just as with the fly ash, the peaks corresponding to gold are there to negate possible charging of the sample. The FTIR spectrum of BA63 is presented on this slide, and as the two investigated materials are both BCAs coming from exact same source, it is expected of them to have a somewhat similar composition. More than half of the peaks identified from both of the samples are either appearing at the same bands or close enough to be associated with the exact same chemical functionality. The two outermost peaks and another two in the middle were ascribed to the stretching and bending vibrations of the OH bond, and the band appearing at 1722 reciprocal centimeters was, just as with the fly ash, ascribed to the C-double-O bond. However, here are where the similarities end, as the wave number associated with the asymmetric and symmetric, respectively, vibrations of the silica O present themselves at approximately 1100 and 840 reciprocal centimeters. This lack of a red shift, or rather the spot-on placement of the wave numbers, suggests that the silica oxide formations are to be without aluminum in a more pure form. Another difference from the FA might become apparent if reascribing some of the mentioned peaks to other functionalities that might be present within BA63. For instance, the wave number at 1630 reciprocal centimeters might suggest the C-double-C bond found in graphite, graphene, and graphene oxides. And interestingly enough, the bond just over 1100 can also be reascribed to the CO bond from graphene oxides. We also utilize the Raman spectroscopy as a complementary technique for the FTIR. The D and the G bands carbon are easily identifiable from the spectrum, leading to the conclusion that the sp2 hybridization state of the carbon is prevalent over the sp3 hybridization state. We have additionally run the analysis, run the XRD analysis on it, and the results are presented on this slide. The main peaks visible in the figure have been attributed to the presence of crystalline carbon and to a lesser extent of crystalline silica, which is in good agreement with the information gathered from previous analysis. And the broad peaks on the left have been ascribed to amorphous carbon, quartz, and mullet, and the peaks on the right from the main peak denote the presence of calcium carbonate and some more quartz. Moving on, however, to one of the most conventional characteristics of any adsorbent, the BET surface area. And as mentioned previously, the BET surface area of BCAs is about 2 to 6 square meters per gram. However, the specific surface area of our second material is approximately 2.6 square meters per gram. The BJH cumulative pore volume is calculated at about 0.01 centimeter cube per gram, and the average pore diameter was estimated at about 21.5 nanometers. With the T-plot micropore area taking up 1.6 square meters per gram. The low surface area of this extracted carbon compared to other conventional adsorbents is probably due to the lack of activation for the capturing media. We are, however, looking into various pathways for physical and chemical activation in order to enhance this parameter. Having extensively discussed the characterization of the materials, let's now talk about the experiments, the equilibrium and the kinetic studies that we have carried out. So despite the minuscule surface area, our waste-derived and unactivated carbon has a respectable capture capacity of 0.73 millimole per gram under atmospheric pressure and room temperature, whereas the benchmark for post-combustion adsorbents is 2 millimole per gram at the same conditions, with these specific surface areas for commercial activated carbons or zeolites being much larger. Additionally, we have looked into determining the effect of temperature on the equilibrium capacity, and here, as expected, the uptake follows the general trend for adsorbents to perform better at lower temperatures with the kinetics following the pseudo second order with an R-squared value of over 0.999 for the investigated isotopes. We will also, in the upcoming days, investigate the influence of flow rate and gas composition on the adsorption of our BA63, as well as look into the issues of mass transfer. And in order to do that, we are currently building a lab-scale fixed bed adsorption reactor, the schematics for which are depicted in the slide. We have designed and HAZOPed the rig, as well as ordered all of the parts, and are currently in the process of assembling the reactor. In the unit, we will be analyzing a range of materials derived from biomass combustion ash, such as the zeolites and the carbons, whilst varying the temperature, the pressure, the flow rate, the gas composition, bed length, and the particle size. I hope this slide helps to outline the goals that we have set out to accomplish. A quick recap. We're going to look into the pathways towards activating the waste-derived carbon and synthesizing zeolites from the fly ash. Then we will characterize our resulting materials and finally conduct the equilibrium and kinetics, as well as the mass transfer experimental campaigns for our biomass combustion ash derived adsorbents. I'd also like to note that our research group has written an extensive technical review paper on the surface functional groups, their benefits and drawbacks, the mechanisms of CO2 adsorption on them, as well as the methods of introducing them. The paper is currently available following the DOI scene on the screen, and not to brag, but it has been the most downloaded article in the last 90 days from the Micropores and Mesoporous Materials Journal. We would like to thank both UKCCSRC and UKRI for helping us carry out our research. And with that, I'd like to thank you for your attention, and let's come to the Q&A.
Okay, we have time now for questions. We have Luis. Luis, do you want to speak up? Okay, he wants me to read out. Oh, yeah. So how was direct carbonation of the ash measured, Mike?
I'm not sure what does that mean, to be fully honest, Luis. We have conducted it using thermogravimetric analyzer, if that is what you're asking. I'm not exactly sure how was it measured. We did put a flow of CO2 over it. We have both tried wet and dry direct carbonation. Sorry, I'm not fully understanding what you mean here by measured. I hope what I've said answers at least partially. Yes, to see if carbonation took place. We have run a TGA, we have put it into a TGA analyzer and supplied CO2 over it to notice if there was a mass change on it, a weight gain, so it would have absorbed the carbon dioxide from the passing gas.
Okay, thank you, Louise. Do we have any further questions? We've just got about 10 minutes for more questions. Probably I'll just ask a general question. What's the potential, or I mean, for fly ash, generally the potential for fly ash and bottom ash, the wider implication generally?
Well, they are currently used already a lot in various industries and in the second applications of them. But as I said in the first slide, the properties of them do not render them unstable or unusable for the usage in other industries. And within carbon capture and storage, there is a lot of different options. And zeolite synthesis, for example, is a very good option. The activation of carbon, or just carbon, the ones that we're doing now. Plus, we're also, direct carbonation, then again, as what Louise said. There are various options right now, but I think the key point about this material is it is available on site of biomass combustion power plants, and therefore there is a potential for in situ decarbonization of them, which is great. And additionally, it's waste valorization, so it could be interesting for the companies to first and foremost lose the landfilling costs and create a product out of it.
Okay, thanks, Mike. Do we have further questions?
So this is Maya here from Imperial College. Just a question about if you've looked into sort of the cost implications. So do you know, do you have a sense on the cost of your material versus other sort of commercial materials? And is there, can you comment on the benefits in terms of cost savings or anything like that?
Unfortunately, we have not yet finished with the whole process, so we don't have exact numbers now. But I think that I think that if first and foremost the carbon is yet unactivated now, so we cannot compare it to activated carbons, for example, that are commercially available. But we were also going to be looking into ways to minimize the cost of activation to try to make our material even more desirable. Plus, I do think that the lack of the landfilling costs and logistics cost is gonna attract additional traction, let's call it that way, for for the proposed materials.
Great, thank you.
So, I'm sorry, unfortunately, we are perhaps maybe in the early stages. As of now, we don't have any rough numbers to report yet.
Yeah, I guess it's something to do, like, I guess, for future work. When you're kind of near the end of the project, you can kind of then think about estimating these types of things. Yeah.
You're absolutely correct. And one of the reasons why we want to look into various ways, for example, both the physical and chemical activation, is to compare the not only the capturing properties of the resulting material, but also the cost effectiveness. That was perhaps one of the reasons why we abandoned our idea of direct carbonation with additives, because it did not yield good economically results. It would not be a good option to do that on an industrial scale. Therefore, we moved on to finding other better options. Hopefully, we're on the path now.
Okay, thanks, Mike. We just have 5 minutes for maybe 1 or 2 questions. Okay, so Mike, what are some of the general challenges that you're facing in the research anyway?
Oh, well, COVID-19.
And
yes.
What are you doing to try to overcome some of those challenges as well?
Mask. But jokes aside, of course, there are a lot of things to be done on adsorption as a technique for carbon capture and storage. It's not yet at the technology readiness level. There's not desired for a wider implementation. One of the things that we're doing is building a lab scale reactor to try to come closer to the reality of things, to go from the TGA apparatus, sort of proof of concept ideas, to more experimental and more real life examples and real life numbers. For example, it's going back to what Mai was saying there with the costs and real life perhaps prices for calculating real life prices per ton of CO2 captured. So there's a lot to be done. I perhaps not very humbly believe that we are somewhat on the forefront of the adsorption process now, trying to look into ways to do it properly. And well, I guess except for scaling up from lab to greater and greater things, there is not much work can be done now.
Okay, thanks very much, Mike, for your presentation. I'll just hand over to Karis now.
So yeah, I just wanted to say a big thank you to both Caroline and Mike for some really interesting presentations from you both today. It's great for our community and for us to kind of hear about some of the research we're funding, because we don't always get the opportunity to hear about what you guys are up to on a day-to-day basis. That was really interesting, thank you. And thank you as well to Gloria for chairing for us today as well, and for everyone's questions. So just to give a quick update on what we've got coming up next week. So next week we've got Aaron Gota from Committee on Climate Change coming to talk to us, and he'll be giving us an overview of the CCC's sixth carbon budget and its recommendations for CCUS. So that's what we've got coming up next week, and that'll be the same time, so Thursdays 2 till 3. So it'll be great to see as many of you as possible next week, and thank you everyone for today.